Hello again. We're going to discuss the functional group amide and also how it is produced and its properties. Well, amides have a functional group of CONH. Now, those of you who do biology, perhaps you're familiar with this functional group as a peptide functional group in polypeptides and proteins. But in chemistry, they are referred to as amide functional group. Why? Because whereas in amino acids, of course, you have carboxylic acid on one side and amine on the other side, and the amine of one amino acid reacts with the carboxylic of another, forming that functional group. In chemistry, you could have a dicarboxylic acid and a diamine. So for example, you could have COOH, CH2 in the middle, and then COOH over here. I mean, obviously this is not an amino acid. And you could have a diamine, like for example, CH2, if I write amine functional groups like that, so this is methane diamine. So when these guys react with one another and water molecule is lost, what do we have? CONH. The same functional group that you saw and you refer to as a peptide linkage in polypeptides. In chemistry, they are referred to as amides. And of course, if you have a difunctional group such as this, then the amine of that hydrogen over there will react with the carboxylic of another one, a dicarboxylic on the other side, and then these reactions will continue, and this would be an example of condensation polymerization, and they are referred to as polyamide. Polyamides, a very famous example of polyamides, of course, is nylon. So in nylon, you have CH2 4 times, C double bond O, either Cl or OH. We'll talk about the acyl chlorides in a minute. And then if you have hexane diamine, CH2, I was thinking about number 6. Because that's repeated 6 times, and then you have NH2 and NH2 over there. So if you have n number of these, of course, where n is in thousands, don't forget, plus n number of that, what is going to be the repeat unit? Well, from the carboxylic side, OH is lost, isn't it? So you take the OH out, you put a bracket around it, that CH2 is going to, in the middle, is going to remain put. And then you have OH, and these two will react, and so what have you got now on the other side? NH, and then that is attached to CH2 6 times, and then you have NH, and then from that side, what is lost? Hydrogen. You put take the arm out, put N on the other side. And every time these two come together, a water molecule is lost, isn't it? So if n number of these react with n number of that, then n number of water molecule is lost. And this is the repeat unit for nylon 6,6. You know why it is referred to as 6,6? Because on the carboxylic side, you have 6 carbons in total, 4, 5, 6. And on the nitrogen side, we also have 6 carbons. Now, if the CH2 six times is missing in the diamine, then you simply get nylon 6. Yeah, 6 from the carbon side. So you realize there are a few different nylons. So enormously important as a polymer, as a condensation polymer, not addition polymers like polyethylene or polypropene. Or polyvinyl chloride. These are condensation polymerization because functional groups react with one another and something is lost. And usually that something is water. Now, there is another way of actually preparing the amide functional group, and that is with the use of acyl chloride. So instead of carboxylic acid, which any carboxylic acid, R means you can put anything on the other side, because we're just concentrating on carboxylic acid. If we could somehow convert that into RC1OCl, these are referred to as acyl chlorides. They tend to be more reactive than their cousins, the carboxylic acid. So how do we actually prepare them? We use a chlorinating agent like sulfonide chloride, which is in the OCR syllabus. Yeah. And then, of course, when you go to higher level, real chlorinating agent that we use at universities are usually phosphorus pentachloride or phosphorus trichloride. But these guys are very, very nasty chemicals, very, very dangerous indeed. So we just sulfonide chloride, SOCl2, is the one which is, well, in your syllabus, so to speak. And then that results in the preparation of a corresponding acyl chloride plus sulfur dioxide plus hydrochloric acid twice. So now you might be thinking, why are we even bothering with these things? Because this is a relatively nasty piece of work. It's a nasty chemical. Sulfur dioxide gas is also a very bad, very suffocating gas, acidic gas. Of course, a non-metallic oxides are all acidic. If you inhale them, they react with the moisture in your lungs, the alveoli, and turn into acids. And of course, hydrogen chloride as a gas, again, as soon as it reaches some moisture, if you inhale it, it turns into hydrochloric acid, neither of which you want in your lungs. So the reactions have to be done under controlled condition, but then you might be thinking, after I do all of this reaction, then I have to neutralize the medium, get rid of HCl, and then that's nasty, this is nasty, that's nasty. Why bother? Why bother? Because this thing is far more reactive than its cousin. So in reactions, what do we actually, so whereas for example, you might put this under reflux to react with your amine or diamine, this one probably can do it at room temperature. Remember, in industry, they don't do things if they doesn't make economic sense. So if we have, for example, sulfonide chloride, so how does it react with, well, if you react with ammonia, then it will react RCONH2, doesn't it? Can't we refer to this as a primary amide? We couldn't we? Because RCOCl can also react with haloalkane. Remember that one? So what happens here? Well, I beg your pardon, not haloalkane. Primary amine. Primary amine. So you produce RCONH, and the other one is CH3. You see, the amide functional group is there, but this is secondary. And then, of course, if you react that with a not primary but secondary amine, then you produce the tertiary amides. So the reason behind using this acyl chloride is because it's simply more reactive. And in fact, in preparation of nylon, rather than what I suggested, they actually use this rather than the corresponding carboxylic functional group. So that's amides, preparation of amides. These guys are also basic in nature. They can also donate in an acidic environment. They can pick up a proton and turn into a corresponding salt. So if you reacted that, or if you put some hydrochloric acid in that medium, or in that medium hydrochloric acid was present, then this will turn into, so you will have another hydrogen there. And don't forget, when the dative covalent bond forms, when lone pair is lost, don't forget to put the plus charge there. And of course, if this is plus charge, and if you use hydrochloric acid, then don't forget to put the Cl- next to it, because this obviously will turn into a corresponding salt. If you don't want to have the salt, then you have, if an HCl is in the medium, present in the medium, then you have to make sure that HCl is removed. Under alkali condition, you can actually remove HCl. So your amide will remain intact. And that is amide. In the next lesson, I will report for you, I will talk about hydrolysis of some complex compounds that have amide and esteric functional groups. They will almost definitely come on your exam papers in the summer. And when they do, we are looking at least 3 to 4 marks. So pay attention to the next lesson as well. All right, thank you.